Hello students, today I am going to discuss a very important problem based on the conservation of energy and force balance, that is, find out the minimum velocity imparted to a mass tied with inextensible thread to just complete circular motion in vertical plane. Also calculate the tension in the string and the velocity of the mass at different position as given in the diagram. As you can see the diagram, here we have a mass that is small m, and I have tied this mass with an inextensible thread, and I am trying to make this string and the mass assembly move in circular path in vertical circular motion. I have the small demonstration. The actual setup is something like this. We have a mass, and this mass is tied with an inextensible thread, and I want to calculate the minimum velocity given to the mass at lowest point for which it can just complete the vertical circular motion. Suppose I am not giving the sufficient velocity at the lower point, the object will return like this. It will not complete the circle. There will be a minimum velocity. If I give that velocity, the object will just complete the vertical circular motion. For example, if I am giving a smaller velocity than that critical velocity, the object will return back to its original position or the lowest point, and the string becomes slack before reaching the highest vertical point. So to just complete the vertical circular motion, we need to provide it a minimum velocity. Today in this topic, I am going to discuss the minimum velocity at the lowest point, also the velocity of the particle at different position of its path. I want to calculate the velocity at the point B, that is at 90 degree from the lowest point, at highest point, and a point that is between the highest and lowest point. Suppose this point, at this point, the string is making angle theta with the vertical. So we will use two concepts in this to solve this problem. First one is the law of conservation of mechanical energy, and second is the laws of motion. We will calculate the tension in the string at different points and also the velocity at different points. All 4 points A, B, C and D. We will deal it one by one. We will start from the point A. The concept behind this problem is the mass should just complete the vertical circle. So we can approximate that when the mass will be at the highest point, the string have tension tending to 0. The string will become just slack at highest point. That will be the limiting condition. If the velocity at which the string becomes just slack at highest point is more than this minimum velocity, the object will be able to complete the vertical circular motion. So we will start considering this concept from the lowest point A. Suppose I am going to do all the problems. First we consider at point A and point D, the lowermost point and uppermost point. Okay, so consider point A. Consider point A and point D. That is the lowermost point and the uppermost point. At the lowermost point, if I draw the force balance, if I consider all the forces, those are acting on the mass when it was at lowermost point. So tension will be in upward direction toward the center of the path. The centrifugal force, that will be mv naught square divided by L, where L is the length of the string, and the weight of the ball at downward direction. At the lowermost point, the forces will be balanced. The tension will balance the centrifugal force and the weight. So we can put down the equation. Tension at the point A, we can say TA. This is the tension at point A, and velocity at lowermost point is V0. So we can say TA is equal to mg plus mv0 square divided by L. We consider this as equation 1. Now, if I consider the highest point, that is point D, at this point, the weight of the object will be in downward direction, tension at point D will be in downward direction, and centrifugal force will be in upward direction, that will be mv2 square upon L. So we can write down the force balance at uppermost point, that is mv2 square upon L, that is equal to mg plus tension at point D. We can take this as equation number 2. Now, as I have already discussed, there should be the minimum velocity for which the string will become just slack at the uppermost point. So we can take the limiting case for which the tension at the uppermost point will become 0. We can take the tension at the highest point as tending to 0. By this, we can say mv2 square mv2 square divided by L is equal to mg. We can say m will be cancelled out and the v2 square upon L is equal to z, or we can say v2 is equal to root Lg. This is the velocity at highest point for which the string will just become slack and the mass will be able to just complete the vertical circular motion. Now consider the point A and D, again. We apply the conservation of mechanical energy for point A and point D. For that, we consider the point A as the zero potential line, ZPL. Zero potential line means this is the datum line at which the potential can be taken as 0. And as the concept of law of conservation of mechanical energy says, for the conservative forces, the sum of kinetic energy and potential energy remains conserved at all points of the conservative force field. So as the gravity is a conservative force field, so we can say the sum of the kinetic energy and potential energy at point A and at the point D will be same. To apply conservation of mechanical energy, for point A and D. We will put the total kinetic energy and potential energy at point A equal to the total kinetic energy and potential energy at point B. So we can write like this: half mv0 square, that is kinetic energy at point A, plus 0, because point A is at 0 potential line or the lowermost point, so potential energy at lowermost point will be 0. That will be equal to the kinetic energy at highermost point, that is half mv2 square, plus with respect to this point the height of this point is L plus L equal to the diameter of this circular path, that is 2L. So we can say the mg into 2L like this. So half m v naught square will be equal to half m v2 square plus 2mg into L. We can cancel out the mass from both sides of the equation and apply the whole equation with the by the 2. So we will get v naught square is equal to v2 square plus 4gl. Now, as we know, we have already calculated by the condition applied before, the velocity at highermost point to just complete the circle is under root Lg. So we can say v2 square is equal to Lg. We place the value of v2 in this equation. Suppose this is the equation number, I think next one. So this one is the second one. I think this is the third equation. So I can place the value of v2 in this equation. And v naught will comes out gl plus 4gl, that is v naught is equal to under root 5gl. So this is the first answer of our first question, first part of the question, that is this will be the minimum velocity that will be required by the ball to just complete its circular motion. Now I want to calculate the tension at the lowermost point. So for that we again go to the first equation, that is Ta is equal to mg plus mv naught square by L. We will put the value of v naught, that is the velocity at the lowermost point, and we will get the tension at the lowermost point. So the tension at the lowermost point Ta is equal to mg plus mv naught square by L. Place the value of v naught in this equation, and tension at the lowermost point in the string will be mg plus, that is m v naught square is equal to 5gl divided by L. L and L cancel out. The tension at the lowermost point will be 6mg. So we can say the tension at the lowermost point in the string will be 6 times of the weight of the ball. Now by the same logic we will calculate the velocity and the tension in the string at other points of the circular path. For that we will again consider the diagram. Now we will consider the point B now we will consider the point at point B. Now again we will do the same exercise. We will find out the force balance and the conservation of mechanical energy between the point A and the point B. So at point B, first of all we will write the force balance equation. Here the tension in the string will be always towards the center, that is TB, and the centrifugal force will be centrally outward, that will be mv1 square divided by F. And the weight of the string will be, the weight of the mass will be in downward direction, that is mg. Now, as there is no motion along the radial direction, the tension in the string will be balanced by the centrifugal force. So we can say that TB is equal to mv1 square divided by L. I can consider this is the question number 5, I think. Not question number 5, this is equation number 5, I think. And again we will apply the conservation of mechanical energy between point A and point B, and we will equate the sum of kinetic energy and potential energy at point A with the sum of kinetic energy and potential energy at point B. Then now we will write the energy balance equation, that is half mv0 square, that is the kinetic energy at lowermost point, plus potential energy is 0 at lowermost point, that will be equal to half mv1 square plus, now point B is at the height of L with respect to zero potential line or with respect to dotted line, so we can say potential energy will be mgl. Now this equation will be v0 square divided by 2 is equal to v1 square by 2 plus gl. Put the value of v0 that we have already calculated under root 5 is here, so it will become 5 gl divided by 2 is equal to v1 square by 2 plus gl. Now as we solve this equation, it comes out 5 gl is equal to v1 square plus 2 gl, and as we calculate the velocity at point B will become v1 is equal to under root 3 gl. This is the velocity at any point, that is at 90-degree angle with respect to the dotted line. Now as we have calculated the v1, we can calculate the tension at point B in the string by putting the value of v1 in the equation number 5. So we can just place the value of v1 in equation 5, and the tension comes out, tension T B is equal to m v1 square will be 3gl divided by L cancel out, tension at point B will be 3mg. That is, the tension is decreasing as it was the 6 times of the weight of the mass at lowermost point, and it will become 3 times of the weight of the bob at the point that is at which the string making 90-degree angle with the vertical. Now we are going to calculate the tension and the velocity at point C. This point C is in between the lowermost point and highermost point. We can say this is a general point for which it is making angle theta with the vertical. Now we will redraw this diagram for this specific case, and this will be a general case that will cover all other points. Suppose this was the case. This was the circular path. At this point, this was A, this point was B, and this is point C. At point C, the string is making angle theta with the vertical. Now I want to calculate the velocity at this point. The velocity at this point, that is V2, not B, it was V3. V3. This is V3. And the tension in the string TC. I want to calculate this. For that we will do some construction. Draw a perpendicular at this point like this. The length of the string is L. Suppose this point is A, this point is C, we can say this point is E, and this angle is theta. So we can say the height of point C with respect to datum line, that is point A, will be equal to OA plus OE. The height of the bob from the datum when it is at point C will be OA plus OE. OA is equal to L, and if I consider this triangle OEC, the OE will be L cos theta. So we can say the height of the bob with respect to datum will be L1 plus cos theta. Now I will write the force balance and the applied conservation of mechanical energy between the point A and point C. This will be the direction of centrifugal force, that is mv3 square divided by L. The tensile will be in this direction, and one force, that is mg, weight of the bob, will be in downward direction. That will be downward direction. By geometry, this angle will be theta. Now, I will resolve the weight mg along the radial direction and tangential direction. Then I will get the component of mg in this direction will be mg sin theta, and along the string it will be mg cos theta. So there will be two forces towards the center. One will be mg cos theta, second will be the tension in the string at point C, and that these two forces will be balanced by the centrifugal force mv3 square by L. So we can write the force balance at this point, that will be tension in the string at C plus the component of the weight along the radius, that is mg cos theta, and that will be equal to the mv3 square divided by L. We will consider this as equation number 6. Now we will write down the equation of energy conservation between point A and point C. So the half mv naught square, that is kinetic energy at lowermost point, plus potential energy will be 0 as it is at the datum of the system, and the kinetic energy at point C will be half mv3 square plus the potential energy will be mgh, and the h in this case is L in the bracket 1 plus cos theta. So we can say it will be mg L 1 plus cos theta. Okay, now cancel out the m from both sides of the equation. V naught square by 2 is equal to V3 square by 2 plus GL 1 plus cos theta. I need to calculate the velocity at point C, that is V3. Then V3 comes out under root V naught square minus 2GL 1 plus cos theta. This is the general equation of the velocity at any general point. That means that in that case the string makes theta angle with the vertical. Now I want to calculate the tension at point C. For that I will put the value of V3 in the equation 6. Suppose this is the equation number 7. So I will put the value of velocity at point C
in this force balance equation, that is equation number 6, and we will get the tension at point C. So tension at point C will be mg cos theta Tc, pardon me. The tension will be Tc is equal to mv3 square by L minus mg cos theta. Now put the value of V3 from the equation number 7. The tension at point C will be m V0 square minus 2g L 1 plus cos theta divided by L and minus mg minus mg cos theta. Now I will put the value of V0 from the previous equation. Then tension comes out m V0 square will be 5gl minus 2gl 1 plus cos theta divided by L minus mg cos theta. Now divide the L from the numerator and denominator. The tension at point C will be m into 5g minus 2g 1 plus cos theta minus mg cos theta. Simplify this. Tension at point C will be 5 mgl, not L, pardon me, minus 2 mg 1 plus cos theta minus mg cos theta. Again simplify this. Tension at point C will be 5 mg minus 2 mg, that will be 3 mg, and this one will be minus 3 mg cos theta, that is 2 mg cos theta and plus mg cos theta, that is. So tension at point C will be 3 mg 1 minus cos theta. This is the tension at any general point for which the string is making angle theta with the direction of the vertical direction. Now we can find out all the previous value for different points by putting the different convenient positions, convenient value for the theta. For example, if I say what is the tension at lowermost point, so at lowermost point the theta will be 180 degree. We are calculating the angle from the vertical. So at lowermost point the string will make theta as 180 degree from the vertical direction. So if I place the value of theta in this case as 180 degree, cos theta will be minus 1 and the tension will be 3 mg, and this one will be 1 plus 1, that is 6 mg. That was previously we have calculated. If I want to calculate the velocity at lowermost point, like here, so for that I will place the theta is equal to 180 degree. For 180 cos 180 degree, this will be minus 1, this whole value will become 0, and V3 will be V0, that is under root 50. In the same way we can find out the velocity and tension in the string at different locations for different value of the theta, and the theta is the angle formed by the string with the vertical direction. I hope this session was very lucid to understand, and this is very important problem to that thoroughly clear your concept regarding the force, laws of motion, and the laws of energy conservation. Thank you.